under the cornfields of Iowa, under the highways of Minnesota, under the bottom of Lake Superior, the largest freshwater lake on the surface of the planet by area, there is hidden one of the most spectacular geological events in the history of North America. 1,100,000,000 years ago, the continent began to tear itself apart. Not slowly and imperceptibly, but catastrophically, with lava flows 30 kilometers thick, with volcanism on a scale this planet had not seen before or since within continental crust. The rift ran 2,000 kilometers through the heart of what would eventually become the United States of America. It nearly created a new ocean right through the middle of North America. And then, for reasons that geologists still cannot fully explain, it stopped. This is the story of the failed catastrophe that made a continent. Before we go any further, please subscribe to this channel. Your support really helps us to continue our work. Thank you. There is a peculiar kind of invisibility that affects the most dramatic events in Earth's history. When those events happened long enough ago and were subsequently buried deeply enough by the accumulated sediments of the intervening time. The Midcontinent Rift System, the geological feature hidden beneath the Midwest of the United States, suffers from exactly this kind of invisibility. It is not small. It is not subtle. By almost any measure of geological scale, it is one of the most dramatic features on the North American continent. A scar left by an episode of continental breakup and volcanism that dwarfs anything in the recorded history of the continent's surface. But 90% of it is buried under hundreds of millions of years of younger sedimentary rock, invisible to the naked eye, legible only in the patterns of gravitational and magnetic anomalies that betray the presence of the dense volcanic rocks beneath. Drive across Iowa on Interstate 80, and you are crossing it without knowing it. Fly over Minnesota, and you are looking down at a landscape shaped by it. Stand on the rocky shore of Lake Superior's north coast in Minnesota, and you are, if you know what you are looking at, standing on the exposed edge of a wound that nearly split the continent open 1 billion years ago. The story of the Midcontinent Rift System begins, as so many geological stories do, not on the surface of the Earth but in its interior, in the slow convective motion of the mantle, the vast layer of hot, solid but slowly flowing rock that makes up the bulk of the planet's volume between the thin, brittle crust at the surface and the metallic core at the center. Understanding why the rift happened where it happened and why it happened when it happened requires understanding the state of the planet 1,100,000,000 years ago. A world so alien to modern experience that the comparison to the present requires repeated adjustment of scale and reference frame. 1,100,000,000 years ago, the Earth was approximately 3.5 billion years old, more than 3/4 of its current age. Life had existed for at least 2.5 billion years, but all of it was microscopic. The Great Oxidation Event, which we explored in a previous video on this channel, had occurred approximately 1.3 billion years earlier, and the atmosphere by this time contained significant amounts of free oxygen, perhaps 10% of modern levels. But there were no fish, no insects, no plants, no animals of any kind. The most complex organisms on Earth were multicellular algae and microbial mats. The continents looked nothing like the map we know today. They had been assembling and disassembling through the processes of plate tectonics for billions of years. And in the time period relevant to our story, they were coalescing into a configuration that geologists call the supercontinent Rodinia. At the center of Rodinia, occupying what is now the heart of North America, was the ancient continental nucleus called Laurentia, the Precambrian craton that forms the geological foundation of most of Canada and the northern United States, some of the oldest and most stable rock on Earth. The Laurentian craton was not a place of obvious geological drama in the centuries leading up to the rift. The craton, the word comes from the Greek for strength or power, is by definition the stable, ancient, tectonically quiescent core of a continent, the part that has not been significantly deformed or metamorphosed for hundreds of millions or billions of years. Cratons are the geological equivalent of the load-bearing walls of a building, the parts that don't move, that don't change, that provide the structural foundation for everything built around them. The Laurentian craton had been geologically stable, by and large, for hundreds of millions of years before the rift began. And then, something happened in the mantle beneath it. That something was a mantle plume, a column of anomalously hot mantle material rising from deep within the Earth's interior, possibly from the boundary between the mantle and the core, carrying heat from the deep Earth toward the surface at a rate faster than the normal background convective flow of the mantle. Mantle plumes are the geological mechanism responsible for hotspot volcanism, the kind of volcanism that creates oceanic island chains like Hawaii, and that created the enormous flood basalt provinces like the Siberian Traps, the Deccan Traps, and the Columbia River basalts that punctuate the geological record of the past 300 million years with catastrophic volcanic events. A mantle plume arriving beneath a continent is one of the most geologically powerful events possible. It delivers an enormous quantity of heat to the base of the continental crust, causing the crust to dome upward, thin, and eventually crack, while simultaneously providing the thermal energy for the massive outpouring of basaltic magma that characterizes large igneous provinces. The plume that arrived beneath Laurentia approximately 1,100,000,000 years ago was, by the evidence preserved in the rocks it produced, exceptionally large and exceptionally hot. Research published in the journal Geology in 2022 by Prasanna Gunawardana, Robert Mucha, Tyrone Rooney, Seth Stein, and colleagues at Syracuse University, Wayne State University, and Michigan State University, used detailed modeling of the mantle conditions required to produce the observed volume of flood basalt in the Midcontinent Rift, to conclude that the event was, as the paper's title describes it, a coincidental rendezvous of a plume with a rift. The extraordinarily large magma volume requiring not just active rifting, but the simultaneous arrival of an unusually large and hot mantle plume at precisely the location where the continental crust had already begun to weaken. The Midcontinent Rift was not merely a rift. It was the product of two simultaneous processes: crustal extension and mantle plume impingement, arriving at the same place at the same time, producing a combined geological event far more dramatic than either process alone would have generated. The rifting itself, the mechanical tearing of the continental crust along the line that would eventually become the Midcontinent Rift System, was part of a broader pattern of continental reorganization occurring at this time in Earth's history. The supercontinent Rodinia was in the process of assembling, and the margins of Laurentia were experiencing the compressional and extensional forces associated with plate collisions and rifting events on multiple fronts simultaneously. The specific geometry of the Midcontinent Rift, its arc shape running from what is now Kansas northward through Iowa and Minnesota, then curving through Lake Superior, then splitting into two arms extending south through Wisconsin and Michigan, reflects the underlying structure of the Laurentian crust and the direction of the extensional forces that were pulling it apart. The rift followed zones of weakness in the ancient Precambrian crust, exploiting boundaries between the different geological provinces that had been sutured together in earlier episodes of continental collision. To understand the scale of what happened next, you need some reference points for comparison. The most active volcanic system on Earth today that operates within continental crust is the East African Rift System, the geological feature that is currently in the early stages of tearing Africa apart, the same kind of process that began the Midcontinent Rift, but that in Africa has not yet progressed to the stage of significant ocean formation. The East African Rift System is approximately 6,000 kilometers long and has been active for approximately 30 million years, producing the Great Rift Valley Lakes, the volcanic peaks of Kilimanjaro and Mount Kenya, and the ongoing volcanic activity of the Ethiopian Afar region. It is one of the most dramatic active geological features on the planet, and it will, over the next tens of millions of years, if it continues its current trajectory, split Africa into two separate landmasses and eventually create a new ocean. The Midcontinent Rift System, at the peak of its activity approximately 1,100,000,000 years ago, was producing lava at rates that would make the modern East African Rift look restrained. The total volume of volcanic rock preserved in the rift, the basalt flows, intrusions, and related igneous rocks that fill the rift basin, has been estimated at approximately 1.3 million cubic kilometers. This is not a number that has intuitive meaning at first glance, so consider it this way. The volume of all the volcanic rock produced by the Hawaiian hotspot over its entire history, the most productive oceanic hotspot on Earth, is approximately 1 million cubic kilometers. The Midcontinent Rift produced more volcanic material in approximately 22 million years than Hawaii has produced in its entire history. The volcanic fields of the Columbia River basalts, which covered much of what is now the Pacific Northwest in lava approximately 16 to 14 million years ago, and which represent one of the most dramatic continental flood basalt events of the past 100 million years, produced approximately 230,000 cubic kilometers of lava. The Midcontinent Rift produced approximately 6 times as much. The individual lava flows that built up the volcanic sequence of the rift varied from a few meters to tens of meters thick, and they accumulated in layer upon layer as successive eruptions buried their predecessors. The total thickness of the volcanic sequence in the center of the rift, beneath Lake Superior, has been estimated at between 20 and 30 kilometers. A stack of basalt lava flows so thick that if you could stand at the bottom of it and look up, the top would be at approximately the altitude at which commercial aircraft fly. This is not the result of a single catastrophic eruption, but of millions of individual flows emplaced over the course of approximately 22 million years. Each flow spreading across the rift floor and the adjacent landscape as fluid basaltic lava before solidifying into the hard, dark rock that still constitutes the dramatic cliffs of the north shore of Lake Superior. The active rift would have been a landscape of extraordinary violence by any human standard. The Rift Valley itself, the topographic depression formed as the crust pulled apart and the floor of the rift dropped along bounding fault systems, was a region of constant seismic activity, punctuated by eruptions that would have dwarfed anything witnessed in recorded human history. The basaltic magma was generated by the partial melting of the rising mantle plume material as it decompressed during its ascent, and it was erupted at temperatures of approximately 1200 degrees Celsius through fissure eruptions along the rift floor. Not the explosive ash-generating eruptions of silica-rich continental volcanoes, but the fluid, fast-moving lava floods characteristic of basaltic volcanism, spreading across the rift floor in sheets of glowing rock that could travel dozens of kilometers from their source before solidifying. The landscape surrounding the active rift would have looked, in broad outline, something like the modern landscape of Iceland, a volcanic island sitting astride the mid-Atlantic ridge, where active rifting and basaltic volcanism are producing the same kind of geological processes that operated in the mid-continent 1 billion years ago, only at a much smaller scale. Iceland gives us our best window into what the active rift looked like. The flat, dark basalt plains. The fissure eruptions sending curtains of fire hundreds of meters into the sky. The lava tubes and pillow basalts forming where lava flows entered standing water. The intense hydrothermal activity as cold water percolated down through the fractured hot basalt and emerged as boiling springs and fumaroles. Multiply the scale of modern Iceland by a factor of several hundred, and you have some approximation of the mid-continent rift at its most active. The world in which this was occurring was, in one important respect, profoundly unlike the modern world. There was nothing living on the land surface. No moss, no lichen, no soil organisms of any kind. The land of Laurentia was bare rock, subject to weathering by rain and wind, but not by biological processes, producing a landscape of raw geological freshness that has no exact modern analogue. The rift eruptions were occurring into this barren landscape, building volcanic mountains and volcanic plains that would have been visible for hundreds of kilometers in every direction. The atmosphere above the rift would have been clouded with volcanic gases, sulfur dioxide, carbon dioxide, water vapor, and the sky above active eruption sites would have been dark with ash and illuminated red by the glow of lava. It was, by any measure, one of the most dramatic landscapes in the history of the North American continent. And it was completely unobserved, because nothing had yet evolved the capacity for observation. The duration of the active rifting and volcanism, approximately 22 million years, from roughly 1,110,000,000 to 1,088,000,000 years ago, is itself worth pausing over. 22 million years is a long time by any human standard, but it is relatively brief by geological standards. The Atlantic Ocean, which opened from a similar rifting process beginning approximately 200 million years ago, has been widening for approximately 200 million years and is now approximately 5,000 kilometers wide at its widest point. The Midcontinent Rift was active for only about 1/10 as long as the Atlantic has been open, which gives you a sense of how early in the process it was when it stopped. The rift had barely begun its oceanic phase when something intervened to shut it down. The critical question, the question that makes the Midcontinent Rift one of the most actively studied and most actively debated geological features in North America, is why it stopped. Failed rifts, or aulocogens as geologists call them, are not uncommon in the geological record. The processes of continental breakup are complex, and not every rift that initiates develops into a mature ocean. But the Midcontinent Rift is unusual in the sheer scale of its volcanism. Most failed rifts produce relatively modest amounts of volcanic material, and in the abruptness of its cessation. The volcanic record shows a pattern of high-intensity volcanism for approximately 22 million years, followed by a rapid transition to a phase of sedimentary basin development as the rift subsided and accumulated sediments, followed by compressional deformation that actually inverted portions of the rift basin, reversing the direction of motion on some of the rift faults and squeezing the sediment-filled basin from the sides rather than pulling it apart. This compressional inversion is one of the most puzzling features of the rift's geological history, because it implies that the extensional forces that had been driving the rifting were not simply removed, but were actually reversed. The region that had been under tension began to experience compression. The most widely accepted explanation for this reversal, and for the termination of the rifting, involves the Grenville orogeny, a major episode of continental collision that was occurring on the southeastern margin of Laurentia at approximately the same time that the Midcontinent Rift was active. The Grenville orogeny resulted from the collision of a landmass with the southeastern margin of Laurentia approximately 1 billion years ago, producing a mountain belt comparable in scale to the modern Himalayas. This collision introduced compressional stress into the interior of the Laurentian craton, stress that was transmitted through the rigid craton from the collision zone on the southeast margin to the rift zone in the interior. The compressional stress from the Grenville collision effectively shut off the extensional stress that had been driving the rifting, and may also have contributed to the inversion of the rift basin that is observed in the geological record. But this explanation is not entirely satisfying to all researchers, and alternative hypotheses have been proposed. One alternative focuses on the plume itself, the mantle plume that had provided the thermal energy for the massive volcanism may simply have exhausted itself or moved away from beneath the rift, removing the heat source that had been driving the crustal thinning and melting. Without the plume, the thinned crust would have begun to cool and strengthen, becoming less susceptible to further extension and more capable of transmitting the compressional stresses from the Grenville collision. Another hypothesis involves changes in the absolute motion of the North American plate. If the plate changed its direction or velocity of motion relative to the underlying mantle, the geometry of the stresses acting on the rift could have changed in ways that favored compression over extension. The 2022 paper by Gunawardena and colleagues at Syracuse and Wayne State University adds an important dimension to this debate. Their modeling results suggest that the unusually large volume of magma in the Midcontinent Rift required the simultaneous occurrence of both active rifting and an anomalously hot mantle plume. Neither process alone could have produced the observed volume of volcanic rock. If this is correct, then the cessation of the volcanism could reflect either the exhaustion of the plume, the end of the rifting, or both. The coincidental nature of the plume rift rendezvous, as the paper's authors describe it, also implies that the extraordinary scale of the Midcontinent Rift volcanism was in some sense a geological accident, the product of a specific coincidence of circumstances that would not have been predicted from either the plate tectonic setting or the mantle conditions alone. The answer to the question of why the rift stopped remains, genuinely and productively, open. It is one of the major unsolved problems in the geology of North America, and it continues to attract research effort from geologists using increasingly sophisticated tools, seismic tomography to image the structure of the crust and mantle beneath the rift, electromagnetic methods to characterize the electrical properties of the buried rift rocks, gravity and magnetic surveying to map the distribution of the dense volcanic rocks beneath the sedimentary cover. The answer, when it came, arrived not from a drill bit, but from a magnetic map, and it reframed the entire geological story of the region. To understand what was left behind when the rift stopped, it helps to think about what the rift was in the process of creating. When a continent rifts apart and eventually breaks to form a new ocean basin, the sequence of events follows a reasonably well understood pattern. First, the continent stretches and thins, forming a rift valley at the surface. Then, as the crust continues to thin, the rift valley subsides below sea level and marine water enters. This is the stage represented by the modern Red Sea, where the African and Arabian plates are separating, and a narrow arm of the sea has entered the rift valley. Eventually, if rifting continues, the two sides of the rift separate far enough that new oceanic crust begins to form at a mid-ocean ridge between them. This is the stage represented by the modern Atlantic Ocean. The Midcontinent Rift had progressed through the first stage. The rift valley was well established, the crust was thinned, and enormous quantities of lava had been erupted. But it had not yet reached the stage of significant marine flooding or ocean formation when it was shut down. The Midcontinent Rift, had it continued, would have followed the same trajectory, the narrow arm widening over tens of millions of years into a full ocean basin. All it needed was another 20 or 30 million years. The Midcontinent Rift had it continued for another 20 to 30 million years, beyond the point where it was stopped, would have reached a stage comparable to the modern Red Sea, a narrow ocean arm extending from what is now Kansas to what is now the eastern end of Lake Superior, with marine water flooding the Rift Valley and new oceanic crust forming at its center. The transition from continental rift to narrow ocean arm is one of the most dramatic transitions in the geology of any region, because it marks the moment when a single landmass becomes two, and when continental processes are replaced by oceanic ones. For the interior of North America, this transition would have been geographically transformative on a scale that is difficult to overstate. Consider what a narrow ocean arm running from Kansas to Michigan would have meant for the subsequent geological and biological history of the continent. The interior of North America would have been divided into eastern and western halves, separated by a seaway that would have been tens of kilometers wide at first and hundreds of kilometers wide after tens of millions of years of continued spreading. The Mississippi River, draining to the Gulf of Mexico, would not exist in its current form. The drainage basin of the central interior would have been divided by the new seaway, with western rivers draining to the Pacific or the Gulf, and eastern rivers draining to the new interior ocean. The Appalachian Mountains on the east, and whatever highland was produced by the Grenville orogeny, would have been separated from the central interior by this ocean, creating conditions for the independent biological evolution of the two halves of what is now a single continental fauna and flora. North America would have been, in its most fundamental geographic sense, two separate continents rather than one. The Rift Valley instead began to fill with sediments derived from the erosion of the surrounding highlands, producing a sequence of sandstones and siltstones that can be seen in outcrops along the shores of Lake Superior, alongside the earlier volcanic rocks. Lake Superior itself is one of the most direct surface expressions of the Midcontinent Rift. The lake occupies a topographic depression whose orientation and geometry closely follow the trend of the rift. The deepest parts of the lake, reaching approximately 405 meters or 1,330 feet in depth, correspond to the center of the rift basin. The spectacular rocky shores of the lake's north coast in Minnesota and the north shore of Ontario, with their dark basalt cliffs rising directly from the water and their layered lava flows visible in cross-section, are exposures of the 1-billion-year-old volcanic rocks that were emplaced during the peak of rift activity and have been exhumed by billions of years of erosion, and most recently by the scouring action of the Pleistocene glaciers that repeatedly covered this region during the ice ages of the past 2 million years. When you look at the Pictured Rocks National Lakeshore in Michigan's Upper Peninsula, those extraordinary colored sandstone cliffs rising from the lake, you are looking at the sedimentary rocks that accumulated in the rift basin after the volcanism ended. When you swim in Lake Superior, you are swimming in a basin whose shape was determined by geological forces that operated 1 billion years ago. The economic significance of the Midcontinent Rift is not merely potential. It has been real and consequential for a very long time, for peoples of the Great Lakes region and for the industrial economy of 19th century America. The connection involves copper, and it is one of the most remarkable stories in the history of North American natural resources. When the basaltic lavas of the Midcontinent Rift were erupted, they contained, like most basaltic lavas, small amounts of copper dissolved in the magma. As the lavas cooled and solidified, this copper was in part exsolved from the cooling rock and carried by hydrothermal fluids, hot water circulating through the fractured and permeable basalt, to sites where it was concentrated in vugs, fractures and amygdules in the rock. The result was the deposition of native copper, metallic copper in its pure elemental form, not bound in a sulfide or oxide mineral, but as the metal itself, in enormous quantities in the basalt flows and associated sedimentary rocks of the Keweenaw Peninsula of Michigan's Upper Peninsula. Native copper deposits are rare worldwide. They require a specific combination of geological circumstances: abundant copper in the source rocks, the right kind of hydrothermal circulation, and the right chemical conditions for copper to be deposited as the metal rather than as a mineral compound. The Keweenaw Peninsula has all of these, thanks to its position at the edge of the Midcontinent Rift, and the result is the largest known deposit of native copper in the world. Single masses of copper weighing hundreds of tons have been found in the Keweenaw mines. The Ontonagon boulder, a mass of native copper weighing approximately 1,765 pounds that was found in the bed of the Ontonagon River in Michigan, was considered sacred by the Ojibwe people and was taken to Washington, D.C. in 1843, where it is now displayed at the Smithsonian Institution. The Ojibwe and their predecessors had known about the Keweenaw copper for thousands of years. The old copper culture, an archaeological tradition of the Great Lakes region that flourished from approximately 3,000 to 1,500 years ago, produced copper tools, weapons, and ornaments of extraordinary technical sophistication, hammering the native copper into shapes that demonstrate a deep, practical understanding of the metal's workability. These peoples were not smelting copper. They were not heating it to melting temperatures, but they understood that native copper could be cold-worked by hammering, and they produced knives, axes, harpoon points, fish hooks, and ornamental objects that show a metalworking tradition of considerable antiquity. The Midcontinent Rift, in this sense, contributed to human cultural development long before Europeans arrived in North America. The industrial exploitation of the Keweenaw copper began in earnest in the 1840s, when the first American geological surveys of the region documented the extent of the copper deposits and triggered a copper rush that brought thousands of miners to the remote and heavily forested Upper Peninsula of Michigan. The Keweenaw copper mines became, in the second half of the 19th century, the most productive copper mines in the world, producing the copper that wired the telegraph networks and electrical systems of industrial America. At the peak of production in the 1860s, the Keweenaw mines were supplying approximately 75% of all the copper produced in the United States. Cities like Calumet and Hancock on the Keweenaw Peninsula grew from wilderness to industrial centers within a generation, their architecture reflecting the sudden wealth that the ancient rift had deposited in the rock beneath them. The copper mines of the Keweenaw Peninsula operated continuously from the 1840s until the 1960s, when the richest ore bodies had been exhausted and competition from lower-cost copper producers in the American West and in South America made continued operation uneconomical. The mines closed, the population of the Keweenaw declined dramatically, and the region entered the long economic stagnation that characterizes many former single-industry mining communities. Today, the remains of the Keweenaw Copper Mining District are preserved as the Keweenaw National Historical Park, and the extraordinary industrial heritage of the region, the steam-powered rock-crushing mills, the shaft houses and engine houses, the company towns with their elaborate social architecture, is being documented and preserved as one of the most significant industrial archaeological sites in North America. The social and cultural history of the Keweenaw Copper Country is as extraordinary as its geological history. The copper boom of the mid-19th century transformed not just the landscape of the Upper Peninsula, but the ethnic composition of the entire Great Lakes region. The mines required labor, enormous quantities of labor, and the mining companies recruited workers from across Europe, producing one of the most ethnically diverse communities in 19th century America in one of its most geographically remote locations. Cornish miners, experienced in the deep rock mining traditions of southwestern England, came to the Keweenaw in the 1840s and 50s, bringing with them their distinctive mining techniques and their food traditions. The Cornish pasty, a meat and vegetable-filled pastry designed to be carried underground as a miner's lunch, became so embedded in the food culture of the Upper Peninsula that it remains a regional specialty to this day. More than a century after the last Cornish miners worked the Keweenaw seams, Finnish immigrants arrived in large numbers in the 1880s and 90s, recruited by the mining companies and drawn by word of mouth through the tight-knit Finnish emigrant communities of the Great Lakes. The Finnish cultural impact on the Upper Peninsula was so profound that the region developed a distinctive Finnish-American culture that persists to the present, expressed in the Finnish-language newspapers that were published in Hancock well into the 20th century, in the Lutheran churches that dot the landscape, and in the sauna culture that became, and to some extent remains, a distinctive social institution of the region. Croatian, Slovenian, Italian, and Polish miners followed, each group adding its cultural layer to the complex social geography of the copper country. The labor history of the Keweenaw is also significant. The copper mines were the site of one of the most tragic episodes in American labor history, the Italian Hall disaster of December 24, 1913, in which someone shouted false alarm of fire at a Christmas party for striking miners' families in the Italian Hall in Calumet, triggering a stampede that killed 73 people, most of them children. The disaster occurred during a bitter strike by the Western Federation of Miners against the Calumet and Hecla Mining Company, and it became one of the defining events of the early American labor movement, commemorated by Woody Guthrie in his song about the Italian Hall tragedy, and remembered as a symbol of the human cost of the industrial exploitation of geological resources. The ancient rift that deposited the copper, the 19th century technology that extracted it, and the human communities that labored to produce it are all part of a single connected story whose roots reach 1 billion years into the geological past. But the mineral significance of the Midcontinent Rift extends beyond the Keweenaw copper. The USGS has been conducting systematic surveys of the mineral resource potential of the buried portions of the rift for several years, driven by the recognition that the same hydrothermal processes that concentrated copper in the exposed Keweenaw rocks almost certainly also operated in the buried portions of the rift, in the rocks beneath Iowa, Minnesota, Wisconsin, and Kansas that have never been mined because they have never been exposed at the surface. The USGS has recently completed new comprehensive geophysical surveys of the rift using gravity, magnetic, and electromagnetic methods, producing three-dimensional models of the rift's structure and composition that are being used to assess its potential for copper, nickel, cobalt, and other critical minerals. The critical minerals angle is particularly significant in the current geopolitical environment, as cobalt and nickel are essential components of the lithium-ion batteries that power electric vehicles. And reducing American dependence on foreign sources of these minerals is a national security priority. The geological legacy of the Midcontinent Rift is not confined to minerals. The rift had a profound influence on the subsequent geological development of the region, and that influence is visible today in the landscape, the hydrology, and the soils of the upper Midwest. The thick sequence of volcanic and sedimentary rocks filling the rift basin created a major structural feature in the crust of the region, a dense, rigid keel of rock that influenced the subsequent deposition of the Paleozoic sedimentary sequences that cover much of the Midwest, creating the basins and arches of the Michigan Basin and the Wisconsin Arch that controlled the distribution of oil, gas, and other resources in the overlying rocks. The rift also influenced the routing of the Pleistocene ice sheets, which followed lines of geological weakness and resistance in the underlying bedrock, contributing to the formation of the Great Lakes in their current configuration. The deep aquifers of much of the upper Midwest, the sandstones of the Jacobsville Formation, and the Orienta sandstone that fill the upper portions of the Rift Basin are major sources of groundwater for communities throughout northern Michigan and Wisconsin. These ancient sandstones, deposited in the Rift Basin after the volcanism ended approximately 1 billion years ago, have been storing water for so long that they represent one of the oldest continuously filled aquifer systems in North America. The water that comes out of a tap in Marquette, Michigan, may have passed through rock that was deposited in the aftermath of the most dramatic geological event in the history of the region 1 billion years ago. The two arms of the rift that extend south from Lake Superior, the western arm running through Minnesota, Iowa, Nebraska, and Kansas, and the eastern arm running through Wisconsin and Michigan, are almost entirely buried beneath Paleozoic and younger sedimentary cover, and are known primarily through geophysical surveys and a relatively small number of deep drill holes that have penetrated the sedimentary cover and sampled the underlying rift rocks. The gravity and magnetic maps of the central United States show the rift as a dramatic linear feature, a zone of high gravity and high magnetic intensity corresponding to the dense, magnetic basaltic rocks of the rift, curving through the otherwise relatively featureless gravity signature of the Paleozoic sedimentary platform. This geophysical signature is so distinctive that the rift was first identified as a coherent geological structure by geophysicists studying regional gravity data in the 1950s and 60s, decades before deep drilling provided direct sampling of the buried rocks. The gravity anomaly reaches amplitudes of up to 70 milligaules above the regional background, large enough that geophysicists in the 1950s first identified the buried rift from gravity data alone, decades before any drill bit confirmed what lay beneath. The magnetic signature is even more striking. The MagSat satellite launched by NASA in 1979 detected the rift clearly from orbit, an invisible geological feature visible from space. The rift that you cannot see driving across Iowa is legible to instruments 250 miles above your head. Here is where the story takes its most unexpected turn. In January of 2026, a research team from the University of Iowa and the University of Minnesota published a paper in Scientific Reports that reframed the Midcontinent Rift from a geological curiosity into a potential energy resource. The billion-year-old failed ocean beneath Iowa may be generating hydrogen, clean, geological hydrogen, right now, in the same rocks that nearly became an ocean floor. The ancient catastrophe that stopped may be about to become useful. The discovery, made by a research team from the University of Iowa and the University of Minnesota, led by geophysicists Mengli Zhang and Yaoguo Li, used the distinctive magnetic signature of serpentinization, the reaction of water with iron and magnesium-rich igneous rocks that produces hydrogen gas as a byproduct, to identify a large zone of hydrogen generation within the deeply buried rift rocks beneath Iowa. Serpentinization is a well-known process in oceanic settings, where it occurs along mid-ocean ridges as seawater circulates through the hot ultramafic rocks of the oceanic mantle. Its occurrence in the buried mid-continent rift rocks is not entirely surprising in retrospect. The rift contains abundant ultramafic and mafic igneous rocks, and over the billion years since the rift was active, water from overlying aquifers has had ample time to percolate down into these rocks and react with them. But the identification of a large and potentially extractable hydrogen reservoir in the Iowa Rift section is a genuinely new finding with significant implications. Natural or geological, hydrogen has attracted substantial scientific and commercial interest in recent years as a potential energy source. Unlike manufactured hydrogen, which requires energy to produce through electrolysis or steam methane reforming, naturally occurring geological hydrogen is generated by geochemical reactions and may be extractable at low cost and with minimal carbon dioxide emissions. The discovery of geological hydrogen sources in several locations around the world, notably in Mali, where a natural hydrogen seep was discovered in the 1980s and has been providing energy to a local village for decades, has stimulated a global search for similar deposits. The identification of a potential geological hydrogen source in the deeply buried rocks of the Midcontinent Rift adds the American Midwest to this list of promising locations and has attracted the attention of both energy companies and the United States Department of Energy. The full extent of the natural hydrogen potential in the Midcontinent Rift is not yet known. The Zhang and Li study identified the serpentinization zone in the Iowa section. Based on geophysical signatures and direct drilling to confirm and characterize the hydrogen system is a logical next step. The natural hydrogen story in the Midcontinent Rift connects the ancient geological history of the region to one of the most actively pursued frontiers of modern energy research. The serpentinization reaction, the reaction of water with olivine and pyroxene minerals in mafic and ultramafic rocks to produce serpentine minerals, magnetite, and hydrogen, has been studied primarily in oceanic settings, where it occurs along mid-ocean ridges and contributes to the deep-sea hydrothermal vent ecosystems that were discovered in the late 1970s. In oceanic settings, serpentinization is driven by the circulation of seawater through the hot rock of the oceanic crust and mantle, and it produces hydrogen that supports chemosynthetic microbial communities at the vent sites. Communities that derive their energy not from sunlight-driven photosynthesis, but from the chemical energy of the hydrogen oxidation reaction. The possibility that similar serpentinization reactions might be occurring in continental settings, in buried igneous rocks within continents rather than at the seafloor, has been recognized for some time, but the geological evidence for significant continental serpentinization and hydrogen generation has been difficult to document. The Zhang and Li 2026 study represents one of the first systematic applications of geophysical methods to identify serpentinization zones in a continental rift setting. The key insight is that serpentinization converts olivine and pyroxene, minerals with relatively low magnetic susceptibility, to magnetite, a strongly magnetic mineral. The serpentinized rock, therefore, has a dramatically higher magnetic susceptibility than the unserpentinized rock, producing a distinctive magnetic signature that can be detected by surface and airborne magnetic surveys. By mapping the magnetic anomalies associated with the Iowa section of the Midcontinent Rift and comparing them with gravity and electromagnetic data, Zhang and Li were able to identify what they interpret as a large volume of serpentinized igneous rock that has been reacting with groundwater percolating down from the overlying aquifers for hundreds of millions of years, potentially generating significant quantities of hydrogen in the process. The economic implications of this finding depend on several factors that are not yet known. The concentration of hydrogen in the pore spaces of the serpentinized rock, the permeability of the rock to hydrogen migration, and the presence of trapping structures that could concentrate the hydrogen to economically extractable levels. But the United States Department of Energy has identified geological hydrogen as a priority research area, and several exploration companies have begun systematic surveys of geological hydrogen potential across the continental United States. The Midcontinent Rift, with its enormous volume of mafic and ultramafic igneous rock and its long history of water-rock interaction, is now recognized as one of the most promising regions for geological hydrogen exploration in North America. The billion-year-old failed ocean may yet power the cars and heat the homes of the 21st century. But the finding illustrates a broader point about the Midcontinent Rift that is easy to lose in the billion-year timescale of its geological history. This is not merely an ancient curiosity, a relic of a world so remote from our own that it seems more like science fiction than science. It is a living geological feature, or at least a feature whose geological legacy continues to shape and potentially resource the present, whose full significance for the American Midwest is still being discovered. Now let me tell you what I think is most interesting about this story. Not just the geology, but the conceptual framework that the Midcontinent Rift offers for thinking about geological time and geological contingency. The Midcontinent Rift is fundamentally a story about failure. The rift failed. It did not complete the process of continental breakup that it had initiated. The ocean that was being created never formed. The two halves of Laurentia that were beginning to separate were forced back together by the compressional stresses of the Grenville collision and the possible cooling of the mantle plume. By the standards of geological processes measured by their ultimate outcomes, whether a rift becomes an ocean, whether a mountain belt grows to Himalayan scale, the Midcontinent Rift was a failure. But consider what that failure produced. The rift failed, but in failing, it left behind 30 kilometers of volcanic rock that constitute one of the world's richest copper deposits. It failed, but in failing, it created the topographic basin that eventually became Lake Superior, the largest freshwater lake by area on Earth's surface, the water source for millions of people, and the ecological foundation of one of the most diverse freshwater ecosystems in the world. It failed, but in failing, it created the dramatic rocky landscape of the North Shore that has drawn painters, photographers, and naturalists to its shores for generations. It failed, but in failing, it preserved in its buried rocks a potential source of clean hydrogen energy for a future civilization that was not even a thought when the rift was active. The contingency of the failure is also worth dwelling on. If the Grenville collision had not occurred when it did, or if it had occurred with slightly less force, or if the mantle plume had been slightly more powerful and long-lived, the rift might have completed its work. The two halves of what is now North America might have separated as fully as Europe and North America have separated, and the geography of the Americas today would have been unrecognizable. The Mississippi Valley might be an ocean. The Appalachians and the Rockies might be on separate continents. The history of human settlement and civilization in North America, which depended critically on the broad agricultural heartland of the Midwest, on the navigable river systems that drain it, on the industrial resources that it contains, would have been entirely different because the heartland itself would not exist. This is not idle speculation about an alternate history. It is a reflection on the degree to which the world we inhabit, its geography, its resources, its ecological character, is the contingent product of geological events whose outcomes were not predetermined. The Midcontinent Rift could have succeeded. It nearly did. The billion-year-old lava flows beneath the cornfields of Iowa are the evidence that the attempt was made. The fact that you can drive across Iowa without noticing anything unusual is the evidence that the attempt failed. And the civilization that relies on Iowa's agricultural productivity and on the copper that wired its electrical infrastructure is the evidence that the failure, in the long run, was not without its rewards. The story of the Midcontinent Rift System is, in microcosm, the story of how the Earth we live on was made. Not by a single grand design executed smoothly to a predetermined outcome, but by a sequence of contingent events, failed experiments, and geological accidents whose cumulative result happens to be the world we know. The ocean that never was left behind a continent that is, and buried 1 billion years deep beneath the fields and highways and cities of the American Midwest, the evidence of what almost happened is still there, readable in magnetic anomalies and gravity maps and lava flows and copper mines and natural hydrogen seeps, waiting for the next geologist to ask what it is trying to tell us. To fully appreciate the scale of what the Midcontinent Rift was producing at the peak of its activity, it helps to compare it not just to modern geological features, but to the record of planetary volcanism in the solar system. The volcanic fields of Mars, including the Tharsis Bulge, home to Olympus Mons and the Tharsis Montes volcanoes, represent the most extensive volcanic province in the solar system. Mars achieved its extraordinary volcanic scale because, unlike Earth, it lacks active plate tectonics, and its mantle plumes have stayed fixed in one location for billions of years, building volcanic structures of dimensions impossible on a tectonically active planet where the moving crust constantly carries the surface away from the underlying heat source. The Midcontinent Rift, operating on a tectonically active Earth with a moving plate, could not achieve Martian dimensions. But in terms of its eruption rates and its lava volumes per unit time and unit length of rift, it was operating at intensities that place it among the most productive volcanic systems in the history of our planet. The chemical composition of the Midcontinent Rift basalts has been studied in detail from the exposed outcrops of the Lake Superior region and from drill cores recovered from the buried portions of the rift. The lavas are predominantly tholeiitic basalts, the iron and magnesium-rich silica-poor rock type characteristic of mantle-derived magmas that have undergone relatively little crustal contamination. This compositional purity is significant. It confirms that the magmas were largely derived directly from the partially melted mantle plume material, rather than being significantly modified by interaction with the continental crust through which they passed. The mantle plume was so hot, and its magmas were rising so rapidly that they transited the continental crust without extensively assimilating the silica-rich crustal material that would have changed their composition. This is consistent with an unusually large and hot plume, exactly the conditions suggested by the Gunawardena et al. 2022 modeling study. The physical character of the individual lava flows in the Lake Superior region has been described in detail in studies going back to the late 19th century and continuing to the present. The flows range from massive, featureless basalt in their interiors, where the lava cooled relatively slowly, producing large crystalline grains visible to the naked eye, to vesicular and amygdaloidal zones at the tops of flows, where gas bubbles were trapped as the upper surface of the flow solidified rapidly in contact with the atmosphere or with overlying water. These gas bubbles, vesicles, were subsequently filled in many cases by secondary minerals precipitated from hydrothermal fluids circulating through the cooled flows. The minerals filling the vesicles, amygdules, include zeolites, prehnite, pumpellite, epidote, chlorite, and most significantly, native copper. The copper-filled amygdules of the Keweenaw basalts are among the most distinctive geological features of the region, and they represent the first stage of the copper enrichment process that eventually produced the concentrated copper deposits that made the Keweenaw so economically significant. The glacial history of the Lake Superior region is itself intimately connected to the geological legacy of the Midcontinent Rift. The Pleistocene ice sheets that repeatedly advanced across the Great Lakes region over the past 2 million years were not geologically neutral. They were powerful erosional agents that stripped away overlying sediments, scoured bedrock surfaces, and fundamentally reshaped the topography of the region. In the Lake Superior Basin, the glaciers encountered the ancient rift rocks, the basalts and gabbros of the 1-billion-year-old volcanic sequence, and found them harder and more resistant to erosion than the surrounding Precambrian metamorphic and granitic rocks. The result was a pattern of differential erosion that deepened the rift basin relative to its surroundings, excavating the modern lake basin to its current dimensions and exposing the dramatic rocky shorelines of the North Shore. The red sandstone cliffs of the Pictured Rocks National Lakeshore on the south shore of Lake Superior in Michigan's Upper Peninsula are an expression of this glacial sculpting. The Pictured Rocks are composed of the Munising Formation sandstone, a sedimentary rock deposited in the Rift Basin after the volcanism ended approximately 1 billion years ago, when rivers and streams were carrying sandy sediment into the subsiding rift depression. The iron oxide minerals in these sandstones produce the extraordinary range of colors: red, orange, yellow, white, green, that give the formation its name and its visual drama. The glaciers carved the cliffs, and the centuries of wave action following the last glaciation shaped the caves, arches, and columns that make Pictured Rocks one of the most visited national parks in the Great Lakes region. The aesthetic landscape that draws tourists today is the joint product of ancient volcanic activity, ancient sedimentation, Pleistocene glaciation, and modern wave erosion, a geological palimpsest written in billion-year-old rock. The Apostle Islands of Wisconsin, just to the west of the Keweenaw Peninsula, are another expression of the glacial shaping of the rift landscape. These 22 islands in the southwestern corner of Lake Superior are composed of the same red Orienta sandstone that forms the Pictured Rocks, and their current form as islands scattered across a shallow embayment in the lake reflects the uneven erosion of the glaciers and the subsequent flooding of the low-lying rift basin as glacial meltwater filled the lake basin at the end of the last ice age. The sea caves carved by wave action into the sandstone cliffs of several of the Apostle Islands are among the most impressive coastal geological features in the Great Lakes region, and they owe their existence ultimately to the billion-year-old sediments deposited in the failing rift. The soils of the Lake Superior region also reflect the geological legacy of the rift. The thin, rocky, nutrient-poor soils of the north shore of Minnesota, the soils that support the boreal forest of spruce, fir, and pine, rather than the more productive deciduous forests and agricultural land found further south, are partly a product of the resistant basaltic bedrock close to the surface. The basalt weathers slowly and produces soils poor in the nutrients that agricultural crops require, which is one reason why the north shore of Minnesota has remained largely forested, while the areas to the south, underlain by deep glacial sediments over more easily weathered bedrock, have been converted to agriculture. The geological character of the Midcontinent Rift rock is thus partly responsible for the ecological character of one of the most distinctive landscapes in North America. The Midcontinent Rift System sits within a broader context of North American geological history that is worth sketching briefly, because it illustrates the degree to which the familiar landscape of the United States is the cumulative product of events stretching back billions of years. The Laurentian Craton, the ancient heart of North America that the rift nearly split, is itself an assemblage of even older geological provinces, sutured together by a series of continent-continent collisions between approximately 2.5 and 1.8 billion years ago. The Trans-Hudson origin, which runs through what is now central Canada and the Dakotas, is the scar of one such collision. The Panochean origin, which runs through Wisconsin and Michigan, is the scar of another. These ancient collision zones, invisible at the surface, buried under the sedimentary cover of the interior platform, represent episodes of mountain building as dramatic as anything in the modern Himalayas, compressed into the geological record of rocks so old that their original structural character is partly obscured by subsequent metamorphism and erosion. The Midcontinent Rift was attempting to disassemble this ancient craton, to undo the work of the Trans-Hudson and Panochean orogenies, and split Laurentia along a line that crossed some of the most ancient and stable rock in North America. The fact that it failed to do so is, in geological terms, a near thing. The rift progressed far enough and for long enough that it clearly had the potential to complete the process. The Grenville collision that shut it down was itself a coincidence of timing, arriving from the east at approximately the right moment to reverse the extensional stresses driving the rift. A few tens of millions of years earlier or later, the outcome might have been different. The broader lesson here is one that runs through the entire geological history of the continent. North America, as we know it, as a single, continent-sized landmass with a broadly habitable interior, a navigable river system, a productive agricultural heartland, and an extraordinary mineral resource base, is the product not of geological inevitability, but of geological contingency. The continent could have been split by the Midcontinent Rift. It could have been flooded by the Cretaceous seaway that actually did divide it, briefly, between approximately 85 and 69 million years ago. It could have been glaciated to a degree that made recovery of the boreal and temperate ecosystems impossible. Each of these outcomes was possible. None of them, in the end, was permanent. And the result of their collective failure to permanently alter the continental character of North America is the geography that shaped the history of the human civilization that eventually arrived here. The story of the Midcontinent Rift is, at its most fundamental level, a story about the Earth as a system that operates on timescales and at scales that dwarf human experience and human history. The billion-year-old lava flows beneath Iowa are older than the first animal with a skeleton. They are older than the first plant that colonized the land surface. They predate, by almost incomprehensible margins, every human civilization, every human language, every human thought. Yet they are not remote from us. They are under our feet. They shaped the landscape we live in. They deposited the copper that wired our electrical systems. They created the lake that provides water for millions of people. And they may yet provide hydrogen to fuel a cleaner energy future. The deep geological past is not past in any meaningful sense. It is the foundation on which everything we know and inhabit is built. The billion-year-old substrate of a civilization that has existed for less than a geological eye blink. Stand on the north shore of Lake Superior on a clear autumn day when the water is dark blue and the birch trees on the rocky shore are yellow and the black basalt cliffs rise from the water with their billion-year-old lava layers exposed in cross-section. You are standing on evidence of a world so different from your own that describing it requires imagination more than knowledge. A world without animals, without plants, without soil, with a sky perhaps hazed by volcanic gases and a sun a little cooler and a little paler than the sun above you now. In that world, a column of hot mantle rock was rising beneath your feet, melting as it came, producing vast quantities of basaltic magma that erupted through the thinning crust and built the rock you are standing on layer by layer over 22 million years. The rock does not know any of this. It simply is. But you, standing on it with the knowledge of what it records, can read it. And in reading it, you can hold in your mind simultaneously the billion-year span of its history and the moment of your own existence, and understand that both are part of the same continuous story. That is what geology gives us. That is what the Midcontinent Rift, buried and invisible and magnificent, has to offer.